one sec. Again, sorry for the abrupt and now what is a late start, but Professor Price and I had some issues with setup this morning, so it'll be all right. I promise. I promise. Great, great stuff. All right, so let me go ahead and pop this up. All right, everybody hopefully can see this. I hope you all had a great Wednesday. And so let's get started. Lord, thank you for bringing us together this morning. Thank you for all the blessings in our lives, Lord. I pray that you would help us to focus, help us to continue strongly through this semester. Help us to fight all the adversity that we come across and just get everything done that we need to. In your name we pray. Amen. Okay. All right. All right. So here we are, September 17th, 2020. Right. We're going to do some stuff. So the lights are going to kick on and off in here, probably the entire class, and be super annoying. It doesn't really affect you guys. That's more of a me problem, not a you problem. So no, Dante, I haven't posted what it's going to be for this week yet. So it's probably going to happen today, right? Since it didn't happen last class. All right, so recap. Rotational equations. Sum of the torque equals J theta double dot. All right, so sum of my torques is equal to my moment of inertia times the angular acceleration of the body, right? And we are assuming that we can pick wherever we like on this, right? We can pick it to be the axis of rotation. You can pick it to be anywhere you want, really. Certain places make more sense than others, right? So just be aware. Reduction, coordinate, acceleration, reducing systems, reduction and reducing systems, right? When I say reduction, when I call it reduction, I am talking about taking what we have, right? Taking what we have and looking at our free body diagrams and writing our equations of motion based off of the mathematical truths that we have identified, right? And so what we want to do, right? What we want to do is we want to say, all right, so if this is a translational problem, I know sum of the forces is equal to mass times x double dot, right? Okay, great. So I need to sum all of my forces. So I look at my free body diagram and I sum all my forces. If you're doing this for a rotational system, then you have to sum all of your torques, right? So the whole process is intertwined, right? The reason I have you do the free body diagram and identify your inputs and your outputs, right? And then do your mathematical truths is because those three steps are setting you up to write those equations, right? Remember, when we write our equations, we won't want anything that's not in terms of our inputs and our outputs, right? We want to try to just keep it strictly in terms of our inputs and our outputs. All right. You guys have any other questions, comments that you want to bring up right now? No? All right. Well, I'm going to clear these, and we'll come back to that later. All right. So Pendulum Lab, for those of you who don't go on Discord, right? I didn't post this in LoudCloud. I apologize, but you may have noticed that I did change the date in LoudCloud, right? Your Pendulum Lab is due tonight, not last night. So if you turned it in yesterday, that's great. And if you didn't, that's okay too, because you can turn it in tonight. So there's that. Right? And then we've got homework 1 due on Sunday. All right. So today is all about doing example problems, right? And to start things off here, we're actually going to do time trials, right? So I'm going to throw you in your breakout rooms again with your groups. Hopefully everybody's already pre-assigned. Doesn't look like it, but I'll assign them and then I will, well, it looks like most everybody is where they should be. If you're not, let me know. But you guys are going to get, let's say 20 minutes to work through this problem, right? We'll do 20 minutes. Same rules apply as usual, right? No check. Obviously, you have to use your computer, but no check, no textbook, right? Just use your notes. We just use our notes. Points, Triquizzer points. Also, this counts as participation for the week, right? So please try. I'll bounce around between your breakout rooms, right? So you're going to want to take down, copy this or take it down, do whatever you got to do, right, for here, right? But this is the problem that you're going to get 20 minutes to solve, right? You got a 2 degree of freedom mechanical system with a damper and a spring in series as shown in figure 1. The independent displacement of the mass is Z1 and Z2, and it's independent. Then there's independent. All right, so let me say that again. The independent displacement of the mass is Z1, and the independent displacement of the node is Z2. Right, is Z2, which is the point between the damper and the spring. The spring is undeflected when Z1 is equal to Z2 is equal to 0, and an external force F applied of T acts on the mass M. Derive the mathematical model for the system. All right, so okay. So everybody good and have the system drawn out with all the parameters that are on the schematic. Right, you're gonna walk through with your groups. Right, call me in when you think you have the answer. Okay, I will bounce around between rooms and answer questions as I go. All right, so there's that. All right, cool. I'm gonna assume that everybody's got them, and I'm opening the rooms. Hold on, I'm closing the rooms. I gotta open them. I'm gonna open them again and make sure I set the timer this time because Dr. D forgot to set the timer. Oh, my bad. Let's try that one more time. People are probably really confused. And Cody Wood can't hear me because he jumped into that. He couldn't stand to be around me that long, and he had to jump into that breakout room. Lickety split. And he's going to make us wait the full 30 seconds before I can reset the timer. I'd like to give you 20 minutes, not 15. All right. While we're waiting, you guys have any questions, comments, concerns about the semester so far? Everybody's working hard. Oh, that's interesting. Okay, I guess I bumped the wire. Did it again. All right, so let's do this. Breakout room closes in 20 minutes. Now you guys can go. I'll be bouncing around. All right. Eddie, which team do you belong in? Right.
Yeah. Okay, there it is.
Sean is a life liver. And Yvette, which team are you in again? I'm blanking.
I've sort of forgot the name, but I know it's the team with Alex and think Kath, I believe. Yeah.
All right. The Zoom engineers?
Yes. Mm-hmm.
Okay, there you go.
Thank you.
Hey, Dawid, what team do you belong in for breakout room? I'm forgetting.
Hey, Professor.
Yeah, what's up, Matt?
For some reason, I'm the only one in my group right now. For some reason, I think I don't know how to pronounce his name. DeWitt is also
Yeah,
in my
Rick
group.
just got here, so I'll pop him in to this. You guys are the stems, right?
Yeah.
There you go. Just work on it and let me know if just let me know if he doesn't show up or anything. But all right.
Okay.
think we're the only ones.
Yeah, we just left the breakout rooms to come back to the meeting to ourselves.
Nice.
What if we're the only ones that finished? That don't seem right. Maybe
No,
we
either that or everyone's just waiting for their breakout rooms to finish, and they probably finished already.
probably.
Oh.
At least we finished. I didn't think we were gonna finish.
Yeah. I'm gonna try to message him, say that we did it, and then tell. I think once he like goes past this problem.
Oh, he's back.
Oh, he's back. Yes, Professor. Come back in so we can show you we did it.
We get our participation points.
Yeah.
Oh, he's not here. Maybe we weren't supposed to leave our breakout room.
Who cares?
Oh,
Oh, there it is. There's a room with other people.
What's up? Everybody
Hello.
Everybody doing all right? All right. I think everybody's back now. Maybe, maybe not. Hopefully. Let's share the screen again. Here we are. Here's our problem, right? Now you guys did pretty well. Everybody was on the right track. A couple of teams got it. So 2 teams will get first and second place, and then everyone else will get third since everybody else tied for third. Because everybody I saw was roughly around the same point, right? And the biggest thing here is how do we handle a massless node, right? And one of the questions that I got was, is there a way that we can combine a damper and a spring that are in series, right? And the short answer to that is no, right? There's not, which is not exactly right? Because we can do some things that we learn later that we might be able to do that and combine the effects of the two. But for right now, we're going to say no, okay? And later we'll talk about impedance in electrical systems, and that'll show us a way that we can combine elements that are not the same, right? We can standardize them in some way. Okay, but that's a later topic. For today, we're gonna say we can't add a damper and a spring in series. Okay, so how do we deal with this, right? How do we deal with this? Well, we'll start the same way that we start everything, right? The free body diagram. And I'm gonna draw this, and this is my massless node, which is not to be confused with this, which is my mass, right? My object. Okay. Notice 1 is a dashed line and it doesn't have the letter M on it, and 1 is a solid line. I know. It's crazy. It's crazy how you can do these things, right? What's happening, right? We've got this applied force here, right? We've got a spring attached here, F sub K, right? And so what have I assumed about this, right? I've made an assumption about this system. I have assumed that the first mass is going to move more, so that I've assumed, right? Assume that Z1 is greater than Z2, right? I've assumed that. How do I know that? By looking at this. Well, I've placed the spring in extension, right? It's pulling back to center. If you were to separate a spring, it would want to come back to center, right? Okay. Remember, spring forces have to be equal and opposite if they're acting on two different bodies, right? They have to be equal and opposite. Otherwise, you have an exploding spring, which is not good. Nobody wants that, right? Nobody wants that. Okay. So cool, right? So can you do this problem and assume that it's in compression? Sure. How does that change it? It's just going to change your signs, right? It's just going to change your signs. At the end of the day, it's going to come out basically the same, right? So if we really wanted to do a KD for this, right? This would be equal to MZ double dot 2. And this one is equal to MZ double dot 1. Okay, but what do we know about the mass of the massless node? What do we know about the mass of the massless node?
It's 0.
It's 0 because it's massless. So if the mass is 0, then mz double dot is also 0, right? So my kinetic diagram is this, where mz double dot is equal to 0. Now, back in statics and dynamics, if you had me, I say that, for statics, right, static equilibrium occurs in one of two cases, right? One where our acceleration is 0, and the other where our mass is 0. One of those things is inherently more exciting than the other, right? And then then nobody laughs because it's not a very good joke, right? But this is when mass is equal to 0. We can draw a free body diagram of something that has no mass. But if it has no mass, then it has no inertia, right? If it has no mass, it has no inertia. There's no force that you need to overcome to start it moving. So my inputs and outputs, what are my inputs and outputs going to be here? Somebody shout out.
Your input force and the output is the position of the mass, I would assume.
Sure. Z1. We'll say it's Z1 and Z2 just for argument's sake, right? But really, we're only really interested in Z1, right? We're not really interested in Z2. You can make an argument for both because as I pull it, there is that relative displacement that you're going to see between the two, right? Okay. So mathematical truths, right? Well, it's a linear system. I'm going to sum my forces, mx double dot. I've got a damper, so I need this guy, and I've got a spring, so I'm going to need that guy. Okay. Cool. That's it. That's all the pieces, right? And I wrote X, right, because I write it as general, but if that's confusing, right, remember we're using Z, so we can always use Z. We always use Z there. All right.
I have one question.
Yeah, so
Isn't the force from the spring going to be proportional to the difference between Z1 and Z2, not the absolute position of Z2, because the damper is capable of moving?
Yeah, I am just writing these as in general, Danny. So sometimes you'll see me write it like this, and sometimes you'll see me, right? It's gonna be the way that I've drawn it. It's actually that, right? And this one is just bz.2, right? Because it's fixed on one end. But yeah, so interchangeable when you're writing your truths. Sometimes you'll see me, the reason I would write it like this, fk is equal to k, z1 minus z2, is to just have it readily available so I don't have to think about it later. But if I were grading something and you wrote kz and then you ended up with z1 minus z2 because it's a free end in your equations, that would be fine too. I'm not going to be a stickler on that as long as you recognize where it changes, right? All right. So let's start the massless with the massless node, right? Just do our due diligence here. So fk minus fb is equal to mz double dot 2, which is equal to 0. And so if I plug in k z1 minus z2 minus b z dot 2 is equal to 0, right? I can do it that way, or I can rewrite this and have bz dot 2 plus k z2 minus z1 equal to 0. Right? You do it either way, right? So what is, all I've done is switch the signs, right? All I've done is switch some signs up. So, okay, right? I mean, that's fine. That's fine. Let's look at the mass, right? So the mass, we've got our applied force minus our spring force is equal to mz double dot 1, right? So I'm going to plug some things in here, right? We'll have mz double dot 1 plus k times z1 minus z2 is equal to f k2. And that's it, right? So this up here we'll call equation 1, and this guy here we'll call equation 2. And it's done. Well, if you wanted to, what you could do, right? Maybe you recognize this already, but from our first equation, right, we get the expression, right, that our sum of forces, that the spring force is just equal to the damping force, right? So we could also write this like this. Right? If I combined by combining 1 and 2. And by combining 1 and 2. So really the takeaway from this, right, what I'd want you guys to take away is a massless node is fine. You can take the free body diagram anywhere, right? That's really it. You can take a free body diagram anywhere. Make sure, right, that, oh, sorry, wrong. Didn't mean to do that. Make sure that you're thinking about the things that you're writing down, right? Make sure you're thinking about the things you're writing down. You guys have any questions on this one? Here's a question. Will there always be some like weird trick that I'm going to throw at you when I tell you to do time trials problems, right? Because so far we did you did the whole preload thing, Dr. D, and then you're talking to us about massless nodes, right? Probably going to have to think about it, right? Probably. Okay. So So that brings us into our example problems from the sheet, right? And so what do we have? We've got this guy and AJ. You're up.
Yo. Yes, sir. Did you want to just see the sheet?
Yeah. Stop sharing. You can.
I have a lot of stuff on there. But... So, got my free body diagrams here, and I just wrote a bunch of notes of stuff that I know about the problem.
So let's
Mathematical truths are.
Let's talk to us about your free body diagram. Walk us through.
It's kind of hard to see from the back, but or from reverse. So I got the first mass, which is like I don't know what to call it, the pinion, I guess. It has a torque that's going clockwise and a theta angle.
Mm-hmm.
And then you have the rack, which has a mass, and then you have your forces acting on it in the different directions based on the torque of the pinion.
Okay. So it looks pretty good. I would say that there's one thing that you're definitely missing there, right? And that's going to be the contact force between the rack and the pinion, right? So that thing, imagine, so a rack is just a gear that's flat, right? It's just a flat metal bar with gear teeth on it. And it interfaces with the pinion, which is just basically a spur gear, right? And those two things touch, right? So at the interface where the teeth touch, we need to have that contact force, because a lot like the problem we did in class with the wind turbine, right? When those things touch, that's how we're driving the system, is through that contact force, right? Okay. But otherwise, good free body diagram. Looks good.
So would that force just be pressing up against the pinion?
Yeah. So it would essentially, if you think about how the teeth interface, right?
Right.
It would just be a single force that's equal and opposite on each of your objects. And it doesn't really matter which way you pick it, because when we put everything back together,
it's gonna cancel out anyways.
Yeah, exactly. So let me pull this up. I'm gonna share screen again real quick and draw the free body diagram, and I'll let you talk us through. Well, you know what, before I do that, why don't we talk about inputs and outputs? What do we got for inputs and outputs?
I didn't get that far.
Well,
I mean, it's pretty easy. I mean, you got, for the input, you have the torque and the pinion.
Well, so if the input's the torque, what are we trying to get out of this system?
The rack to slide across C.
Right. So if we're trying to get it to slide, right, we're trying to get it to do what?
To displace.
Yeah, trying to get, so X is our displacement, right?
Right.
So that's our output, right? So our input's torque. Our output is the displacement X. Okay. So what kind of mathematical truths would you think that we need to have on this?
Well, the first one is the sum of the torque, which is IM times, what is that, angular, omega, is omega dot, yeah, omega dot.
Okay.
So that's the first one.
Sure. J
Then
omega
you have,
is a good one.
right, J omega dot. And then for the some of the forces on the rack, it's the mass times acceleration.
Sure. Yep. So mass times acceleration, right? What else? What other things do we have on that are acting on the pinion, right? That are acting on the translational part of the system.
Then we have the damping of the spring.
So we've got damping, right? And we've got, and it's hard, it's kind of hard to see on this thing that I gave you, right? But you've got the damping and you've got the spring, right? So that damping, that C in the bottom left-hand corner, that's supposed to be the damping. And I'll show it to you guys on share. Thanks, AJ.
Okay.
Question.
Yeah.
Why would C be damping and not just flat friction?
Because the book that I pulled this diagram from uses C as damping coefficient. So in reality, why would it be that instead of friction? Because so you use rack and pinion, you might have heard as rack and pinion steering in your car, right? And typically you want that to be lubricated underneath. You don't want metal on metal contact, right? For smooth steering. So we're assuming that there's some thin film of fluid between the rack and the lower part of the what it's sliding on, right? To minimize dry friction. What about when you look at this, right? What about that I sub M term, right? Why are they telling us about that? Why are they telling us about that? Now you can, we did a trick like this when we were talking about the wind turbine, right? We took all of our inertia and we collapsed it into a single inertia, right? We lumped it all together. And we're kind of doing that again here in this model, right? So the actual inertia here is going to be IM or JM plus JP, right? So these two things are different. I call them J, right? And again, it does, the variable changes, right? They're interchangeable. J and I are interchangeable. B and C end up being interchangeable, right? So I don't want you guys to get confused on the nomenclature. And I'm sorry for flopping between so many different things here, right? But just keep that in mind when we're doing this. Right. So the J that we're using in our equation is actually the combination of JM and JP together. And it's actually JM and JP together. Right? So here's our free body diagram, right? Pretty much, right? AJ, you had all the y direction forces too, so yours is more complete than mine, for sure. But for what we're doing here, we're only going to be analyzing, we're going to assume that this is not going to lift off of where it's sliding, right? So we're assuming the ideal case. And you'll notice that I pretty much keep my free body diagrams in terms of the directions of motion that we're talking about, right? In terms of the directions of motion. Like if we wanted kinetic diagrams, this would be J theta double dot, which is equivalent to J omega dot, right? Those are equivalent statements.
What in this case would be your FSC? Because I see your damping force, but
So FB is damping. FC
Yeah.
is contact between the rack and the pinion, right? That's what that is. And this whole, that this is moving that direction, right? Told that that's moving that direction. So we've got kinetic diagrams. We've got free body diagrams. Everybody cool so far? Everybody feeling all right with this? Where we're at? Right. So we talked about it, right? Our input is that torque, our output is the motion created on the rack, right? So think of it this way. I know this one says it's driven by a motor, but the most common place that you will see a rack and pinion system is the steering in your car, right? So I torque the steering wheel, and then that slides my rack, right, back and forth. And what does that do? Well, that controls the angle of my front tires, right? So it goes back into another rotational system at some point, right? But that's essentially a very simplified version of how that works. There's a lot more to it, right? There is, but the very minimum, you're torquing something and it's creating some translational motion. Right? We talked about our truths, right? So we've got T is equal, some of the torque is J omega dots or J theta double dot. And some of the forces is MX double dot. We've got our spring force, we've got our damping force. And I'm actually going to write this one up here too, just so that we remember that we have this, right? We've got our inertia, our total inertia, J, that we're talking about in this equation is the combination of J sub P and J sub M, right? Because if we go back to I just want to go back here for a sec, right? We're combining these two inertias into a single inertia, right? We're lumping the model. Just going to lump them. Okay. Great. All right, so how do we do this? Right, do you guys want to start with the pinion or you guys want to start with the rack? Where would you start?
Let's start with the pinion.
Pinion?
Sure.
So what should we do? If I'm going to start at the pinion, what do I do? We'll go back up to our equations for a sec. If I can get this computer to work. Nailed it. Oh, no, too far. All right, so just so we're clear, right? These are the equations, the truths that relate to my pinion, and these down here are the ones that relate to the rack, right? So we're starting with the pinion, and then I've got to sum my torques, right? I've got to sum my torques. What do I have acting on this here? Oh man, well, I forgot something on my free body diagram, right? Need that capital R. Okay, so I've got that torque, right? And that torque is acting in the positive direction. But I've also got this force, right? So how do I make this into a torque, right? How do I talk about the torque or the moment that is produced by that force on this system?
We need the radius.
Right, it's just the force times radius, right? You guys ever forget what the mathematical equation for it is? Think about the units, right? The units are Newton meters or foot pounds, right? What do I need to get Newton meters? Well, I need a force and a distance, right? You need that for foot pounds, right? I need a force and a distance. So just keep that in mind. The units bear out with that, right? All right, so is that going to be a positive or a negative torque contributed by the contact force on the pinion?
Should be negative.
It's gonna be negative, right? Because I'm gonna use my fancy moment simulator here, right? Okay. Imagine what my fingers are holding at the center of the gear, right? And I push in the direction of that force. It's going to cause a clockwise rotation, which according to this system would be negative, right? Awesome. Awesome. So we
Be
can
true.
write out, yeah.
To be truly pedantic, the force of the friction is just opposite whatever the force of the torque is. So if it's negative in this case, but in a general model, it's just the opposite of whatever the direction of rotation is.
So that F sub C isn't friction though, Danny. That's a contact force of the teeth on the pin from between the pin and the rack. Right. We're assuming, remember, we're basically not even looking at friction unless it's specifically called out as viscous friction, right? As damping in a lot of these problems. Right. We're trying to
Can you go back to the model?
We're trying to maintain the linearity. All right. What was that? I'm sorry. Didn't hear that. Go back to where?
The model.
The model.
Yeah, I got
this one here.
Yeah.
Free body diagram.
Yeah, looking at this, so we're not talking about the contact force being negative. Yeah, because it's not the torque, since that's heading in the positive direction. What component of this is going to be negative?
Right. right? So this contact force is creating, by me applying a force here, right? If this was not connected to anything else, and you just had a wheel there, right? And you start pushing on the bottom with a known force, that would create a torque about the axis of rotation, right? That would be a negative torque or a negative moment because it's that force times that distance, and it's going in the opposite, in the counterclockwise direction here, because according to this system, clockwise is okay. You good?
So then for the equation, we're just essentially trying to convert that contact force to a torque. So it'd just be FCR in our mathematical model.
Yep.
Okay.
Right. So when we write this out, right, we're going to sum our torques, right? We have a positive applied torque T, a negative torque from, so we have T minus F sub C times R, right? Because remember, the other thing is we need the units to match up when we do these things, right? And if you just put a force in here, then the units don't match. And this is equal to J theta double dot, right? And that's where we're gonna leave that for right now. So we're gonna leave that for right now. This is gonna be one of those systems where we end up combining them after we get both equations, because we want everything in terms of our inputs and our outputs, right? And our contact force probably not going to be known to us, right? In real life. But that's it. That's how we get our opinion, right? So if we move to the rack, well, we've got to use sum of our forces is equal to mass times acceleration, right? So we go back to our free body diagram. Well, I've got the contact force that's acting in the positive direction, right? Because I have positive left according to my diagram. I've got negative FB and negative FK. Okay. So let's deal with that. Okay. So I'll have mx double dot is equal to negative fk minus f sub b plus f sub c. Let me write it how I have it on the drawing. F sub c. So I'll plug in my other mathematical truths, right? So mx double dot is equal to negative k times x minus b x dot plus f sub c, right? And then finally, we can leave this as mx double dot plus b x dot plus kx is equal to my contact force, right? Call that equation 2. And so I think it's pretty obvious what we would do with this, right? But we're going to do it anyway. We're going to combine these two things, right? We already have something that is solved for f sub c. So we're going to plug that, we're going to plug equation 2 into equation 1, right? We're going to plug equation 2 into equation. So let's go ahead and do that. Right? So I'll end up with T minus mx double dot plus b x dot plus k times r is equal to j theta double dot. Okay, that's a thing, right? That's a thing. And we could certainly leave it like that, right? Kind of, maybe. Well, what did we say our input was, right? We defined our input to be t, and our output, we defined it to be x, right? So, yeah. But unfortunately, we've got t and x and theta. So we need to convert theta into x. Conversely, you could also say my input is t and my output is theta, and convert all of your x's to thetas, right? It doesn't really matter, but we're gonna do it anyway, right? We said x, we defined it as x, so there should be an x in there, right? There should be this x right here times r. All right, so how do I do this, right? How do I get theta? How do I convert theta to x? How do I convert theta to x? Well, remember, we talked about this a little bit. X is equal to r times theta, right? And if you take the derivative of that, it's that. And if you take the derivative of that, you get this. So if I have theta double dot, right? Can't I just solve this equation and say, well, theta double dot is equal to 1 over r x double dot, and plug that in? T minus m x double dot plus b x dot plus k x times r. This would be capital R, right? In our case, make it correct. Is equal to j over r x double dot. All right, and so now we can algebra some things, right? Now we're going to algebra some things. So I'll have t is equal to m plus j. It's mr plus j over r x double dot, right? So if I multiply through by r, I'll end up with mr x double dot negative because the whole thing is, this whole quantity is being subtracted. So I bring it over, I end up with j over r plus m times r x double dot, right? So that's where this comes from. All right, well, negative br x dot, well, that's plus b r x dot plus k r. And there we have it. T in terms, all of our inputs on one side, all of our outputs on the other. In a similar fashion, right, we could write this in terms of, if we really wanted to, right, if we really wanted to, we could say, you know what, though, I really want to know this, the torque, how the torque affects that angle, right, that we're twisting through. Right, and so in this case, I would take my x double dot, and once I get to this point, it's just changing these variables, right? So j over r. Well, x double dot is just r theta double dot, and this would cancel. Okay. Going too fast. J r theta double dot. R theta dot plus k r times r. Okay. And so we could simplify this, and we could also get a model in terms of theta if we wanted, which would be mr squared plus j theta double dot b r squared theta dot plus k r squared. That's just a change in dynamic variable, right? Theta and x are both dynamic variables. What makes them a dynamic variable is that they're time dependent, right? They change with time. So you can swap them in and out. We just need to remember this, right? This is like the Rosetta Stone for getting things shifted around here. And that comes from the fact that, like, we derived it in ESG-360. If you took that, no biomeds, you didn't take it. But all mechanicals and Bachelor of Science Engineering students, you did, right? If you roll a wheel, if you roll a circular object, it's going to travel a linear distance. How can we define that? Well, if it goes one complete rotation, it's going to travel the circumference of the circle, right? And so we can take the ratio of the angle that it's traveled to the distance that it goes compared to the full circumference, right? Divided by 2 pi. And you'll find out that x is equal to r theta. That's something that comes out of the dynamics of the problem. Okay. You guys have any questions on this one? Okay. Everybody doing all right? Yeah, maybe. Stop asking me if I'm doing all right. Doesn't make me feel any better.
My main question would just be, so should we just assume that we're automatically going to be neglecting the whatever component that was that the torque was operating around and just focusing on the pinion?
So we didn't ignore anything, Sean. It's just that we end up just combining both. Like you need both halves of the equation to make the full equation, right? You need both halves of the system and combine them. The reason that we don't leave it, and a lot of the systems that we're going to talk about, we will leave them as two separate equations or three or more, right? But the reason that we didn't in this case is because in practice, determining the contact force between two gears is difficult, right? Because you could try to put a sensor there, but it's going to wear out really quickly. And it's just not a practical solution, right? And so from a modeling standpoint, since we're not going to know that contact force, we need to get it in terms of something that we do know, right? And it's much more plausible that we would be able to track either the position of the rack or the position of the pinion itself, right? Any other questions? Good. Well, there's no more questions on this one. Then, Azael, you can have the stage here. You have the main stage. Thanks, AJ.
Okay, so this is what I have for my free body diagram, or both. I don't know if you can see it.
I mean, that looks good to me.
And then I have the inputs and the outputs.
Mhm.
Okay.
Okay.
And then the truths.
And so mathematical truths, we're looking at Newton's second law for rotation. You've got some change in position, right, for your spring. All right, so let's talk about that damper, right? Let's talk about that damper. Is that damper a free end or is it fixed end?
The free end.
It's free end, right?
Oh.
So you need to account for that with your equations, right? The other thing that I would say is if you're going to use theta P and theta D in your free body diagram, make sure that translates into your mathematical truths, right? Call out the variables that are on the free body diagram. Don't use different ones. It'll just for systems like this where it's not really that difficult to discern which one is which. It's fine, but for things that get more complex and have multiple angles and multiple positions and things, if you can draw it back directly to your free body diagram, it's significantly more helpful. Right? Okay. But so far, so good.
So that look better.
So yeah, do something like that, right?
Well then I have the reduced equations.
Spring again, right? So your spring. Is that between theta? Is that between JP and JD, or is that someplace else? Is there a different angle that's causing the rotation of that spring?
Oh yeah, it's 5 feet.
Yes. All right.
So would it be like this?
Yes, that's what that's what we want to do.
Okay. So in that case, I have to change my reduce equations. So
Right. So that's going to change your equations up a little bit, I assume. Right. Now, again, for things like on an exam or anything like that, right? Like homework exam, if you mess up a little bit, that's fine. I will take that last part, right? I'll take your equations that you wrote down and I'll check to see if that is what your model looks like, right? So I'll use the stuff that you give me. So make sure that you guys can't stress this enough, right? Can't stress this enough. Make sure that you're showing all of your work on everything that you do. Sure you show all of your work on everything that you do. I understand that not everybody has the nicest handwriting. Believe me, I am guilty of that as well, right? And I understand that sometimes you do work in different places, but I would also highly encourage you to do things in a sequential manner at the very least, right? I can't control your handwriting. And I'm not going to force you guys to take like penmanship classes or anything, right? But please make sure I can like at least read it, right? Like if I can't read it, it's not like oh, he can't read it, so he'll just assume that it's right. No, that's not typically how it works. So make sure I can read it, and if you can, please try to just be as sequential as possible with your work so that it kind of like leaves a trail. So I don't have to, I mean, I will if I have to. I will hunt through your paper and try to make sense of it, but I would greatly appreciate it. I would greatly appreciate it if you guys could just go sequentially. Anyway. All right, so Azael, thank you. That was, got us most of the way there. If you keep working on it and you want to share the new equations with us, that's fine. But let's talk about this, right, for everybody here. What do we have here, right? This is, and again, so I understand that these problems leave us wanting in terms of the things like there's no problem statement, right? There's just variables on a page, right? And I get that, I get it. But here what we've got going on is you're rotating this spring by some angle phi, right? That causes the disc P I guess we're going to call it the piston P to rotate, which then in turn causes the disc D to rotate, right? So I have some initial rotation by phi here, right? Now the rotation of K, right? The rotation of K depends completely on phi and theta P, right? The amount of torque that this spring is going to produce depends on the relative motion between these two things, right? It's a free end. The amount of motion in our damper, right? And so again, this book, this resource, you see, I'm going to use B when we talk about it, right? B torsional, B sub T, both sides of it are moving. So the entire damping, the damping torque provided is going to be generated by the relative velocity on both sides, right? Okay. So if we get to our free body diagram, right? Azael had this. I figured I'd draw it too, just to have it up here. Right. And I'm going to assume a couple of things here. What I've assumed is that phi is greater than theta P, and that theta P is greater than theta T. Now, notice, and I want you guys to see this here specifically. The damping acts oppositely to the motion. It doesn't have to do with the input torque or the spring torque, right? It acts oppositely to the motion. we have assumed by writing our coordinate systems here, we're going to assume that everything is moving in the positive direction while we're doing the problem, right? And then if our signs come out the other way, that will inform us that we chose poorly, right? But we're going to assume that everything is moving in the direction that I've indicated here, right? Which is why TB is fighting TK here, and which is why TB is moving opposite. Well, no, that's, but let me back up. The reason that this one's acting with theta D here is because they have to be equal and opposite on both ends, right? They are connected on both ends, right? So internal forces trump what is supposed to happen, right? If you have a fixed end damper, it's got to be opposite the direction of the spring. Now, why did I draw it this way? Well, I assumed that theta P was greater than theta D, and in turn, also assumed that theta dot P is greater than theta dot. Okay. So I assume, what does that mean for me, right? Well, it means that the one side is moving faster than the other, so the other side's got to try to catch up, right? And so we're actually getting some extension in our damper, right? We're getting some extension in our damper. Okay. So free body diagram, right? What if, again, what if you chose TB to be in the opposite direction that I have it here? That's fine too. Just make sure it's equal and opposite on the other disk, right? Whenever we have two things connected, we have to talk about the internal forces. Internal forces are always equal and opposite. The thing that is coupling this system together right now is that damper, right? The thing that is coupling this together is the damper. Okay. Ins and outs, talked about it, right? My input is going to be phi. My output, I'm going to have two of them, right? Theta P and theta D. We have our mathematical truths, right? So I've got sum of my torques is equal to J theta double dot. I've got my damper is going to be B theta dot P minus theta dot D. And I've got my spring is K P minus theta P, right? And that's where we ended up. Right, so where should we go from now? We've got choices, right? We can either do J sub P or J sub D.
Can you go back for 2 seconds?
Where, Dante? What do you mean to go back to?
The truths.
Remember, the mathematical truths are just identifying the elements of the system, right? Whatever elements that I have in my system, I need a mathematical truth for that. Right? That's is what it is. That's what I need. So if I have a spring, I need my spring equation. Right? We're specifically told that this uses K sub T, right? So that's a torsional spring. Specifically told that. Okay. Cool. Do we have any other questions so far? Is everybody doing okay? No? All right. So do we want to start with J sub P or J sub D? What do you guys want? Pick your poison.
D.
D? All right. J sub D. All right, so we're going to start with J sub D, meaning we need to sum our torques, right? So let's go look at J sub D. All right, so I'm going to sum my torques here. Okay. So what are my torques on disk D? It's just TB. Just TB. All right, so that one seems, we can get there. That one seems pretty simple, right? So it's going to be JD theta double dot D is equal to TB, which is equal to B theta P minus theta dot D, theta dots, not theta, excuse me, theta dot P minus theta dot D. So JD theta double dot D plus B times theta dot D minus theta dot P, right? I just did some fancy algebra, right? Because really this becomes JD theta double dot D minus B theta dot P minus theta dot D, right? But zero. But I just algebra that, right? Multiplied through by the negative and just flips the signs. Cool. And that's fine. If you left it like that, that would be okay, right? But this seems like a good time to talk about a global and a local, right? So what is the input on this disk, right? On JD, the input to that disk, right? If I was just looking there, well, that's going to be the rotation of P, right? That's going to be theta P. So you could technically, if you wanted to, right? It wouldn't be less or more correct. You could rewrite this as JD, we'll call this one, JD theta double dot D plus B theta dot D is equal to B. You could write it like that. And we could go one further, right? And we could simplify this to a first order system. JD omega D omega dot D plus B omega D equal to B omega P. If you want.
So would that only be in the case that we're attempting to, I guess, reduce our overall outputs and make everything in terms of a single output, or what would that be for?
Why would we want to switch dynamic variable? Is that, or why would we want to set it up so that theta D is a function of theta P?
Second one.
So the reason you might want to do this is if you wanted to just analyze half of the system, right? So when we get to time domain analysis, if I just use this, right? If I wanted to, right? If I wanted to, I could use just this equation and write a Laplace transform for it and analyze just what would happen to the output angle of my disk based off the input angle of that piston P, right? So I can break this apart and analyze it however I would like. Or you can keep them all together as one system of equations and either make a Laplace transform or a state space equation that would allow you to analyze the entire system as a whole, right? But it's okay to break it down into pieces for analysis purposes.
So Dr. D, would you, I know you had mentioned global versus local. Would you explain that one more time, like what the importance was or how we're using it in this example?
All right, so if we go back to our free body diagram, right? Hold on, I'll get it. The computer will behave for a second. Please and thank you. All right, so overall, my input to this system is phi, right? I'm gonna go back all the way to this schematic. All right, so the overall input, right? The overall input to this system is here. That I am putting in some angle, right? I'm displacing everything. Now, if I look, don't look at that D, that disk D, right? Don't look at that. Just look at how it's connected to I sub P, okay? If we look just J sub P, right? If we look just at this, the local, right? And when I say local, I mean, I can break the system up into pieces, right? They're all coupled together in this case, right? They're coupled together by this damper, right? But I can ignore the effect of that theta D, right? And I can say, well, locally to just J sub P, I have the input of phi and the output of theta P, right? Then if I come back and I ignore that spring, I can look at just the second portion, right? And locally, I have some input theta P and some output theta D. right? But on the whole, from end to end, throughout the entire system as a whole, I'm going to twist this and I'm going to get this and this as my outputs, right? I'm going to twist this by phi and I will get theta p and theta d as my outputs on the whole. But it's okay and it's appropriate to want to analyze just half of a system, right? It's okay. Maybe you're just interested in how much theta d moves based on how theta p moves, right? You're not really too concerned about what the actual input angle is, right? Maybe. It's hard to tell when all you get is a picture and no description of what this is actually, right? But yeah, that's the difference between a local and a global. Global means we're looking at the entire system as a whole. Local means if I'm just looking at one portion of it, what are my inputs and my outputs? So that one was pretty easy, right? There's only a torque on there. So we got that. And we'll roll with this one, right? So again, if you can get it to here, I'm happy. If you get it to here, that's okay too. And if you wanted to do that, right, that's fine. So let's do J sub P.
So, never mind. I'm gonna let you do it.
No, what's up?
I guess so. For our first equation, should we have just left the torque on, or the dampening torque on the other side, since we can just plug it back in? Or should we not assume?
Saying like, no, so you always want to have inputs on one side, outputs on the other, right? So this equation one, as I've written it, it's all outputs, right? There's no global input on here, right? So this is equation one is written as if the global input doesn't exist, because in fact, if you look just at that chunk, you don't directly see phi, right? Phi gets coupled through everything through the spring, right? The effect of me torquing the front is due to how much the spring moves, right? Which transfers into a spring torque, which then transfers into the motion of P, which then transfers into the motion of D. Okay, so equation one is written in an input-output format in which we've considered just the global variables, right? We've said globally, these are my outputs, and my input is not existent on this part of the system. Okay. When we look at J sub P, what we're going to see is that you're going to have phi there, right? Because phi is coupled to it through that spring. Now, the red boxed one is, okay, well, I don't like having a zero there, right? Because it makes it weird. So I'm going to write this in terms of my local inputs and outputs, right? And locally, my output is theta D and my input is theta P. Does that make sense?
Yeah.
Sweet. All right, so J sub P. So what are we going to do? What are our torques on J sub P, right? Well, we'll go back to the free body diagram again. Slowly, so I don't bleed slides, right? Well, okay. What do I have? What are my torques here?
TB and TK.
Yep. TB and TK, right? TK is positive, TB is negative. Okay, thank you. So we're going to sum our torques. Summing our torques gets us JP theta double dot P equal to TK minus T. Okay, so if I plug in what I got on my, I plug in from my mathematical truths. I'll get this. right? So this is going to tell us that I want all of my p's on one side and all of my thetas on the other, right? Because we're going to write this in terms of global inputs and outputs. So I'll have to do a little bit of algebra, right? J theta double dot p plus b theta dot p minus theta dot d plus k theta.
Is it incorrect to write TB minus TK? Is that,
What's that now? What?
can you explain why it's the TK minus TB instead of TB minus TK?
I can. I will explain it right here. TK is positive and TB is negative, right? We've assumed that positive rotation is going in the direction of the motion here, right? So this follows and then that is opposing. So again, I said this on Tuesday. I keep wanting to say Monday, but it was Tuesday. I said this on Tuesday. I'm going to say it again in a slightly different way. God did not create coordinate systems. Man created coordinate systems to try to describe what God created. Okay? They are arbitrary. They are human made. You can pick it to be whatever you want. I will check your work based on the coordinate system that you put on the paper. If you don't put one on the paper, then I'm going to use whichever one makes most sense to me. Okay? So you should just put one on the paper. Put one on the paper. All right, cool. So here we are. We're here, right? We've got K theta P, and this is equal to K times phi. And yeah, I'm just gonna throw a 2 after that and leave it alone because I've got all my theta P's and theta D's on one side and all my P's on the other. And that's that. You guys have any questions?
Where did the equals K phi come from?
From here. So you distribute the K into this, right? You'll get what? You'll get P minus K theta P. Right?
Thank you.
Yep. You guys remember like when your teachers would tell you that you're never going to need algebra ever again in your real life? I'm gonna look right at the camera right now. You look at me. They lied right to your face. They lied right to your face.
My childhood dreams just got crushed.
Yeah, I'm sorry. It's soul crushing. But also seriously though, doing things like balancing checkbook or figuring out a budget, right? That's algebra. Really. That's what it is. All right. You're like balancing a checkbook. All that's handled online. I don't even know what a checkbook looks like. Like a book, check marks in it. I don't know. Bad joke. Anyways, my dad's coming in.
Can you move on?
You got any questions on this one?
Yeah, I do.
Yeah, what's up?
Can you explain, I'm sure you did earlier, but the TK value that you started with at the beginning, where you equated to phi minus theta P?
Yes.
Can you explain it one more time?
I can. Sure can. All right. Let's go back one more. I think it'll be better here. Okay. Let's talk about it here, right? So I've got this input of theta, right? So imagine for a second, I've got draw it a little bit bigger, right? I've got this spring here, right? This guy, right? And I'm going to twist the front end by phi, okay? But the back end is attached to this disc, right? And that disc
Okay.
is moving by theta p.
Gotcha.
So the total displacement of that spring angularly is the relative position, the relative angle that we've twisted through, right? It's a lot easier to conceptualize this with linear or translational motion, right? And the example that I've been using that I really like is imagine you had two toy Matchbox cars, right? And one had a spring on its bumper attached to the nose of the one behind it, right? If I move them both the same amount, that spring distance hasn't changed at all, right? But if I move the front one by 2 inches and the back one by 1, I have a net displacement of 1 inch, right? So I'm in extension. Likewise, if I move the front one 1 inch and the rear one by 2, I now have a net compression of 1 inch, right? So when we're talking about springs with a free or a fixed end, right? When we have free end springs, we have to determine how much did it move on the front end and how much did it move on the back end, right? And so those assumptions that I wrote down help me to understand which way I should be drawing my torques, right? Because if P is greater than theta P, right? What does that mean? Now I'm going to try to draw this, and it's probably going to turn out horribly, but we're going to try anyway, right? So imagine if I'm looking at the spring head on, right? And we'll assume that I can draw this based off of, right? Here's my spring, right? This is a cross section of the wire. It's all of the wires are behind it, right? Kind of see where I'm getting at here, right? So in the initial state, right? Say this is undeflected, right? But I'm going to apply some position here, right? And this angle, we'll call that phi, right? And that's the front end, right? That's what the front looks like. But the back is moving at a different rate, right? And it hasn't moved as much as, so I'm going to actually draw this a little bit more exaggerated, right? So here is that, right? I drew it the same angle because that was a good idea. Right? So this has moved from my starting position by feet, right? But I have my other spring, and my other spring's not, my other end of the spring isn't moving as much, right? So this only rotates through theta p. Well, I've got this extension now in the spring, right? I've separated the coils, right? And so I've got this net, we'll call it extension because it's separating the coils. Whereas if I had assumed that theta p was larger, right? If I had assumed that theta p was larger, it would have extended to here. And this would have caused a compression of my coils, right? It would have pushed the coils into one another. And I realize this is not drawn great, right? And you really have to use your imagination to figure out what's going on here. But this depends on the direction of which I apply my torque, right? Because in this case, right, where theta p is less than phi, I've got some extension. So this wants to actually fight back, right? We want, but did I draw this the wrong way now? Maybe I assumed it wrong. So we got TK going one way. Right? So TK is fighting the motion, right? It's fighting if we're extending the spring, if we're opening up the coils, it's going to want to fight us. I think I wrote my assumption in the wrong direction for now that I'm looking at this way. Oops, my bad. So what Dr. D really assumed was the other way. So if theta is greater than theta p, right? That's going to open it up. But if the rear one is more, then we're going to have, yeah, so I drew my pretty sure I drew it the wrong way. Yeah. So our equations are going to be slightly wrong. What I actually drew is that. Okay. Because they pushed the spring into compression and now it wants to go in the direction of theta P, right? That's what it wants to do. Okay. Torsional springs are rough. They are. So that's going to change our equations a little bit, right? Because now this isn't there. This is like this, right? So it doesn't affect the JD equations. It just affects JP. And that's where the effect comes in. So where did it affect it? We had to switch the signs on our K. Essentially, we had it just in the wrong direction, right? What's the penalty for sign errors? Is like half a point. So Dr. D loses half a point for this lecture. I'm okay with that. I'm okay with that. I'll add it to my running tab. Yes, I'll add it to my running tab. Sign errors are the least of your concerns for right now. All right, so what does it do? I flipped the sign. Could I have also flipped the torque direction, right? Sure, but that's also going to flip the sign. Right? It's going to make this negative instead of positive. Okay.
I did have one more question before you move on. I'm sorry.
Yeah, go for it.
So why is it that on JD you wrote the equation based off of the so that way the output was on one side, but this JP is not written that way? The equation, the final equation.
So AJ, can you say that one more time? You cut out a little bit.
Yeah, I'm sorry. Why is it that JD is the equation for JD is in terms of the output, but JP is not?
Okay, so why is JP in terms of JD?
Yeah.
Why is there no input there? Is that what you're like? No global input? Why is P not included in JD? Is that what your question is?
Yeah. Well, we changed JD around so that way on the equal other side of the equal sign it was a B theta P.
Yeah.
But how come we didn't do that for JP?
Okay, so why didn't I move? Gotcha. I got you. So why did I leave theta D here?
Right.
Yeah. Because so the equation 2 is written in terms of global inputs and outputs, right? So globally, my input, I called out my input as phi, and I have two outputs, right? I've got theta P and theta T. Could you do it in terms of local inputs and outputs? Sure. You could throw theta D on the other side. It wouldn't be that big of a deal. But for this, that's the reason I left it there, is because technically theta dot D is a global output, right? So this is a global equation saying, hey, I've got some phi and this is going to give me some theta P and theta D, right? The other thing that we could do, which would be really gross, and I'm going to tell you, please don't do it, but some of you will try to do it anyway. You could solve this for theta dot D, right? And try to plug it into equation 1, which I would not recommend doing. I think that would be a big mistake. And so don't do it. Later, when we get to Laplace transforms, that'll be made a lot easier. Okay. Cool. Any other questions?
Yeah, I just have some clarifying ones I want to make sure. So the TB, we're writing that in because we're assuming it's the friction of fluid.
wait for it. Yeah, one more. One more. So we write that TB, right? Why are we writing that TB? Well, we're writing this TB because we actually have a specific damper called out.
Oh, it's a damper.
Right?
Right.
So we have a torsional damper called out. You'll see a lot of these problems, they'll tell you, right? It'll say, oh, hey, look, there's some damping in here, or hey, look, it'll be like the rack and pinion one, right? There's a very little C in the bottom corner that was trying to indicate to you that there was some damping there. So be aware. Really look at the schematics and see what's included. Now, in problems like that are not in class problems, like homeworks, right? You guys have probably noticed that there are problem statements that tell you a little bit about the system, right? So for some of them, when it's not obviously apparent. So I try to make it clear, at the very least on exams, what exactly you need to be solving for. Right?
And can you just explain again? I get it, but I just want to like hear it again. Why the TBs are in opposite directions on the free bodies?
Because it's an internal torque based off of a physical thing, right? So it's the same deal with the spring, right? We are cutting, when we do our free body diagram, we are cutting this piece out, right? So there's some reaction force that is provided by that damper. Some reaction force provided by that damper. So if you pick it in one direction on one side, you have to pick it in the opposite direction on the other because it's a physical damper that's there, right? It's a link between the two things, and the internal forces have to be equal and opposite, otherwise explosion, right? We don't like our systems to be flying apart from one another.
Right. Got it. Thank you. Oh, and then one more quick thing. Why are we, I know it's for the damper, but why are we putting a dot above the theta for theta P and theta D?
For which one?
Just
For
like
here?
right there.
For my assumption or for what?
For, yeah, assumption.
Because this determines, it's kind of like the spring, right? So a damper is a function of the velocity, right? And so if one side's moving with one velocity and one side's moving with the other velocity, right, you have to determine what is the relative velocity between those two, right? So again, if the front Matchbox car was moving at 10 meters per second, which would be ridiculously fast for a Matchbox car, but we're going to say it anyway, right? And the back one was moving at 5, there would be a net damping force between the two if I had a shock there of 5 meters per second, right? You would have moved the net velocity, right? So it's think about it this way, right? The thing that's connecting the two is going to have, I don't want to put this right. So if you were standing on the damper, right, you would view yourself moving at whatever the difference is between both sides, velocity wise, right? So we're always defining things with a free end based off of the relative velocity, right? The relative velocity of that object.
Got it. In terms of velocity.
Cool. Anything else? All right, I'm having a feeling that this is probably going to be the last one we get to today. Don't worry, I will post at the end of the week when I put up homework solutions. You'll get all of these problems worked out, right? It'll be super cool. So don't worry about that. So we'll do this one, and Nicole, you are up.
Okay, so
Hold on. Sorry, let me.
no, you're good.
I have to give you the main stage. That's my bad.
Okay, so here is my free body diagram. I don't know if you can see it. And then I have the inputs off to the side. And then the like true mathematical truths right there. I'm not like super confident with the output just because with the like with the thetas, I know the directions are different. So I wasn't sure on that part.
Okay. All right. So we've got three. You've got three, essentially three pieces, right? Here, you've got that J1, that first gear set, right? You've got the other gear, right? J2. We'll call that J2, and then you've got well, the other gear, and then you've got that inertia J2, right? So there's a couple of ways that we can do this, right? The way that you did it is fine, right? You got J1 and you got your torque and you've got your contact force, and then the one's moving in the opposite direction, so you have your contact force and your spring torque, right? And then on your third one, you have the spring torque and the damper, right? And your spring torques were equal and opposite, right? Traveling in the opposite directions, and so that was fine. That looks good. The other thing that we can do is we can create an equivalent system for this in which we combine the total inertia of that first gear set into one thing, which can be done, but we haven't really gone over that so far. But your free body diagram looked good. It looked really good. So in terms of inputs and outputs, what do we have? What's our input?
Oh, I had it as the T1.
Okay. What about output? What do you have as the output?
I had it as theta 1, 2, and 3, but I don't know.
Sure. So for this, depending on how you do it, you can either have it as I would either have it as theta 2 and or theta 1 and theta 3, or theta 2 and theta 3. And the reason is, if you're going to use it do it as an equivalent system where you lump some of these inertias together, then you don't have to worry about it. And the reason why it becomes an equivalent system is because of that gear ratio, right? Because we know that if I have a specific torque that I'm inputting, I know how that would transfer, right? I know how that would scale onto the second gear via the gear ratio. But yeah, good stuff. What about mathematical truths? What do you have for that?
So the sum of the torques with J theta double dot, and then TK equals K, and then theta 2 minus theta 3, and then for the damper, just K theta.
K theta for the damper. So remember, dampers scale with velocity, right? So it should be a function of theta dot. Right?
Okay.
And it should be B or C theta dot. Good stuff. Okay. Cool. Thank you. I'm gonna switch back to sharing. I'll draw some of the stuff we talked about, right? Good stuff. Good stuff. So let's talk about what this is doing, right? I'm gonna change some of these things here, right? Just because I can. So we've got this initial inertia that I'm applying a torque to, and that's going to rotate through some angle, right? And then that's going to cause the other gear to turn, right? And this is funky, right? Because if we assume it's an ideal gear train, right, then that second gear doesn't have an inertia, right? But it's got its own angle that it's turning through, and theta 3 also has its own angle that it is turning through. And I've said, well, hey, you can combine some of these things together, right? Well, technically, we could, right? Now we'll talk about doing it. We'll talk about why and how. Let's talk about why. Okay. So what do I've got, right? I've got this guy and this. So let's start with, I'm going to draw it a little bit better. Let's start with this, right? So this is J1, right? And J1 has some angle theta 1, right? And we apply some torque T1, and we have some contact force, F sub C, right? Okay. Then we've got gear 2 here, right? Which does not have an inertia associated with it. Theta 2, right? This is F sub C, and we've got some, I drew it this way, you draw it the other way, it doesn't really matter as long as you're consistent. And then I've got my large drum here, and that's going to have TB, but remember this has theta 3 in the opposite direction. And call that TK. I've got TK going out. Okay. Okay. So let me doesn't make that a different color, so it's obvious that. So something like that. Nicole, you had something similar to that, right? Your assumptions were a little bit different than mine, which is fine. It would still come out. All right. Now, talking about this idea of an equivalent system, right? Well, what would make it equivalent? Well, if I combined, right? What am I talking about combining here? Right? I'm going to take essentially that and make it into one thing, right? Why is that possible, right? Why is that possible? Well, it's possible because of the gear ratio, right? We talked about gear ratio last week, right? And we found out that, you know, the gear ratio, if I know the number, or if I know the gear ratio, I can know how to scale my input velocities or my input position or my input torque, right? And so I can write this in terms, I can write T1 in terms of the gear ratio to tell me what the torque at this other gear would be. And I would just consolidate all of that inertia into a single point, right? And I would say, okay, well, yeah, I have that input torque, but really it's effectively transforming into this other torque, right? So what would that look like if I lumped all of that together, right? We'll draw it down here. Well, if I was to lump all that together, I'm going to have something here that I'm going to call, let's call this J effective, right? And this is now going to be rotating by theta 2, right? It's going to have some torque, which is T1 effective, right? So it's the transformation of my input torque into what it would be after. I just realized that says Jeff. That's funny. So we've got Jeff here, right? This is Jeff, right? Jeff's a nice guy. All right. And we've got we still have our spring right now. Our spring, let me use the same colors so that it's a quick one, right? So we still have our spring torque here, right? That's still going to happen. We're still going to have J2, and J2 doesn't feel as cool anymore, right? Because it doesn't have a name like Jeff. So there's that. But J2 looks exactly the same, right? We haven't done anything to that second inertia. Now, that's theta 3, right? So that's theta 3. Okay. Cool. And again, right, this is predicated on the fact that we can use, you know, our gear ratio. I'll just write it here. Gear ratio is equal to omega 2 over omega 1, or n is equal to theta 2 over theta 1, right? We have this idea of the gear ratio. We know how this is going to scale our torque, right? Torque actually scales with, I believe it's Should be 1 over, well, we'll talk about it in a second. We'll talk about it in a second. I'll derive it. Okay. Okay. So you can do this either way, right? What is the difference? Well, the difference here is that instead of us getting a coupling equation between FC here, we already know the punchline, right? Because we know the gear ratio, we already know the punchline. So we're just eliminating that step. That's what we're doing, right? Because if you did it this way, it would work the same way that this one is going to work. That's why they're equivalent, right? But because you know the gear ratio, you know that all of the dynamics of this part are really designed to just create this torque here, right? We still have the same spring, right? These two things are going to couple through the contact force, right? So we're just saving ourselves a step because we know about gear ratio. So my input is going to be T. In this case, you know, we'll call it T1 effective essentially, right? And my output is going to be what? Well, output's just going to be theta 3 if I do this in the equivalent way, right? Because really, technically, it's theta 2 and theta 3 if you want to get crazy with it. Yeah, but right, I put in some torque and it turns the mass, right? That's what I want. That's what I want, right? So I've said it's equivalent due to the gear ratio, right? Okay. So let's go through our mathematical truths, right? We're going to sum our torques. That's equal to J theta double dot. I've got spring here, and the way that I've drawn it, it's going to be this guy. And I've got some damper, right? And that's going to be this. I can also write another truth that we haven't been using, and this is where something else is going to come into play that we haven't talked about very much yet, right? We're going to use kinetic energy to determine our effective inertia. What is jet, right? How do we define jet? Well, this is how we're going to do it, right? Well, I know that the kinetic energy of this system has to be 1/2 what I'm going to call J1 omega 1 squared plus 1/2 of J2 omega 2 squared. Okay. Well, I can write all of this in terms of omega 2, right? I want to write all of this in terms of omega 2 because I want to consolidate this all down to omega 2, right? Okay. So how do I write this in terms of omega 2? Well, omega 2 is just 1 over n times omega 2, right? So we end up with J1 times 1 over n squared. Let me 1 over n times omega 2 plus 1/2 J2 omega 2 squared. So now I can combine these through algebra, right? And I'll end up with 1/2 times 1 over n squared J1 plus J2 omega 2 squared, right? And that means what to us? Well, that gear J2 doesn't exist, right? It's massless, right? It has no inertia. It's an ideal gear set. So really, this is telling us that this is going to be 0. So our equivalent inertia, right? Our equivalent inertia, right? Because remember, in the general form, kinetic energy is equal to 1/2 times inertia times omega squared, right? Well, that just means that everything in here is Jeff, right? So Jeff is equal to 1/n squared times J. Did everybody follow that? It doesn't matter what the kinetic energy is, okay? It doesn't matter what the actual value for kinetic energy is. What matters is that I have energy is a scalar, so it is a net amount. We have rotational kinetic energy in this system, right? It is defined, the total energy of this system is, well, the part that we're looking at, which is the first mass and the gear, has to be 1/2 J1 omega 1 squared plus 1/2 J2 omega 2 squared. If we go back to where our gear ratio is, right? Wait for it, we'll get there. Our gear ratio is, we're using this, right? We're using omegas. Omega 1 is equal to 1/n times omega 2, right? So I can get everything in terms of omega 2. Why do I want that? Because I have this free body diagram right here, and that's in terms of theta 2, which means if I take the derivative of that, that will be omega 2, okay? So I want everything to collapse down and be in terms of omega 2, okay? Wait for it. Right, so that's why I plug in 1/n times omega 2 for omega 1. Right, so this turns into this via the gear ratio. Okay, what happens here? What's going to happen here? Well, this stays the same. It's already in terms of omega 2, right? Then we just algebra. Then we're just algebraing, right? And so I'm left with 1/n squared J1 plus J2. Now the general form of kinetic energy is this for a rotating system, right? 1/2 of my inertia times the velocity squared, right? Well, this stuff all in here is just my inertia, right? But we know that the J2 term is 0, so Jeff or J effective, J equivalent is 1/n squared J1. Okay. Why is that important? Right? Why is that important? Well, that's going to come in to play at the very end when we want to substitute back in for Jeff in terms of J1, right? But that's how we understand. That's basically how we create the equivalent model. Right? So if you needed to combine inertias, right, for something, and it wasn't obviously apparent how you do it, you use energy and you reduce the equation, right, until you can make one algebraic expression where you can substitute in for one of the variables. Does that make sense-ish? I know I went fast. We're running out of time for today. Okay, keep going. So now we're going to get into the stuff that is more traditional, right? So why don't we start with that first, right? Well, sum the torques on the equivalent free body diagram, right? We're going to use that one. Let's go back. Come on. Here we go. So I'm gonna analyze Jeff first, right? I'm gonna analyze Jeff. And cool, so I'm going to sum the torques on Jeff. What are my torques on Jeff? I've got T1 effective and TK, right? And they're both going to be positive. They're both in the positive direction. It's weird, but let's go with it. All right, so what do I have? I've got J effective theta double dot 2 is equal to T1 effective plus TK. All right, well, T1 effective, K was given as theta 3 minus theta 2, okay. I will move some things around here. All right, notice I've got everything in terms of theta 2 and theta 3, right? So AJ, kind of like your question last time, right? How do you decide where to put what, right? Couldn't you just leave theta 3 on the other side? Sure. Not a huge deal here. Not a huge deal. They're both technically, depending on whether you're writing a global or a local equation, right? Depending on whether you're writing a global or local equation. Okay. So I've got, oh, so that's fine, right? So that's good. I've got everything that I need in terms of what I wrote as inputs and outputs, right? I have theta 2, theta 3, and my effective T1, right? That's all my inputs and all my outputs. I don't have to do anything else here. What if I wanted to know what theta 1 was? Well, you can do that through dynamics, right? But we're not going to do that right now, because this is it. You can just leave this like this. What was the point of finding J effective? Well, if you needed to do an analysis on this, you need to know what J effective is, right? So you need to know how to combine it.
Can you go over that again? How you combine them with the J effective?
Go over how to get J effective?
Yeah, at the end. I mean, once we do the equation, just go over it again.
Yeah, sure. So now we're going to do J2, right? You guys have your free body diagrams in front of you. It's going to take me too long to go back. What do we have on this? Well, the way that I've drawn it, I've got negative TB and negative TK as my torques, right? So J2 theta double dot 3 is equal to negative TB minus TK. J2 theta double dot 3 equal to negative B theta dot 3 minus K theta 3 minus theta 2. J2 theta double dot 3 plus B theta dot 3 plus K theta 3 is equal to K theta 2 theta 2. In terms of theta 3 and theta 2. Again, right? If you're explicitly told, you know what, no, they told me that theta 1 was an output, right? I was explicitly told in a problem statement. So, okay, so that means you need to get all of your theta 2s in terms of theta 1, right? Well, how would you do that? Well, we have the gear ratio, right? We wrote it down on the other page. N was equal to theta 2 over theta 1, right? So if you wanted theta 1, sorry, I wrote that opposite the way that it should be. It's theta 1 over theta 2. No, okay. Dr. D is going bonkers here. N is equal to theta 2 over theta 1. So theta 2 is equal to n theta 1, right? There we go. So you can use this and plug it in to here and to here, right? And you can get everything in terms of theta 1 through the gear ratio. It was asked, we will go over it. How do we find Jeff? Right? How do we find Jeff? Please don't do that. Please. There we go. Okay. how do we find J effective? I want to combine everything from the first mass, right? I know the gear ratio, right? I know the gear ratio. I've been told enough about this system that I can figure out the gear ratio. Okay. So I'm going to write kinetic energy equation, right? My kinetic energy equation Kinetic energy in general is 1/2 J omega squared. I don't know if anybody can see this or not, right? It's written here, right? In the red box, right? That's for a rotational system, right? For a rotational system. If this was a translational system, it'd be 1/2 mv squared. If it was a combined system that had rotation and translation, guess what? It's a scalar. You just add them, right? You can add 1/2 j omega squared plus 1/2 mv squared. That's legal. It's fine. Why? Because the units work out. Okay, the units work out. But anyway, we're working with 1/2 j omega squared here, right? And that's equal to my kinetic energy. Now, I don't care what the value of the kinetic energy is. I just want to combine my two parts of my system, right? So what do I have? I've got this mass here, this rotating inertia, and that's connected via a shaft to some gear, right? And you guys, can we see this? I'm trying to pin my video here, right? And on the other side, I've also got a gear. And that's connected to some other mass right further down. But I'm making a cut. I'm going to make a cut before I even get there, right? I'm just going to make a cut before I even get there. We know that there's some stiffness associated with this still, right? But I want to combine J1, and we'll assume that this gear has J2. We'll just assume for right now that it has J2, right? This whole part right over here, J1 should be moving with omega 1, and J2, we're going to say is moving with omega 2. I have it doesn't matter the direction, right, because this is a scalar, but let's draw it appropriately anyway, right? So I've got some omega 1 that's going to spin the other gear by omega 2, okay? So the total kinetic energy of this half of the system is 1/2 times J1 times omega 1 squared plus 1/2 times J2 times omega 2 squared, right? Okay. Well, that's great, right? That leaves us right here in this part that I'm gonna, right? So is everybody with me to here, right? Kind of, you add the kinetic energy from the first thing and the second, right? They're both moving at different rates.
Why does kinetic energy just make a sudden appearance in this case when it didn't with previous gear ratio problems?
Because in previous gear ratio problems, we didn't combine the system down to a single inertia, right? We did it the long way by using this free body diagram on the top, which is still fine if you'd rather do that, right? But because we have the gear ratio, we know how this is going to transform, right? We know that this this torque will transform via the gear ratio, and we can figure out what it's going to be once it passes through the gear ratio, right? And in order, if we wanted to use this equivalent system, then we have to do it. So you don't have to do it, right? You don't. You can do it the long way and step through, J1, a free body diagram for J1, write your equations, do it for this massless or this inertialess gear over here, and then you can run it all the way through. What you hopefully find out is that you get the same exact model on the back end, right? Why? Because they're equivalent, right? That's the whole idea of equivalence. Okay. But if we want to combine inertias, we need to look at the energy, right? We need to look at the energy. And so we had it up there before, but gear ratio is equal to omega 2 over omega 1, right? Go back and we'll go back and double check so I don't, yeah, so omega 2 over omega 1, right? So gear ratio is omega 2 over omega 1. Okay. So because of that, I can rewrite this, right? I can say, well, I'm really only concerned about what happens after I transform this torque, right? After I get through gear 2. So I want everything in terms of omega 2. So I can solve this and say, well, omega 1 is equal to 1 over n times omega 2. And I'm going to plug that in to my kinetic energy equation, right? And this still equals kinetic energy. And so I'm going to plug that into my kinetic energy equation, right? So now instead of omega 1, I have everything in terms of omega 2. Why am I choosing omega 2? Because I'm concerned with what's leading up to the final portion, right? I want to know what omega 2 is. Okay. So I plug this in. For omega 1, I say, well, that's 1 over n omega 2, right? Then I do some algebra here, right? Then I do some algebra here. And well, that 1 over n squared is just 1 over n squared, and omega 2 squared is just omega 2 squared, right? So I can combine like terms, right? My omega 2 stay here, my 1/2 comes out because everything's being multiplied by 1/2, right? And I'm left with 1 over n squared J1 plus J2. Now this, when compared to my general kinetic energy equation, whatever's inside that parentheses is just my effective inertia, right? Because I have my velocity taken care of. I have that 1/2 taken care of. Everything else describes the inertia. And in fact, if you were to look at the units, right? Inertia plus inertia gives you inertia, right? And so I can write that J effective is this, right? But for this particular case, that second gear doesn't have any inertia. J2 is 0. So J effective is just 1 over n squared J. Now again, you're not feeling confident in using energy to reduce to that, that's fine. You can do it the longer way, right? And you'll have 3 equations and you'll just chain them. It's an equivalent model. An equivalent model. Okay. This was just to serve as another way of showing you guys yet another method that you can do, right, to do these things. All right, you guys have any other questions?
In the 2.5 minutes that we have left, would it be possible to just do a quick run through of what it would look like, what it would look like if we did the three body model?
Unfortunately, I don't think so in 2.5 minutes.
Okay.
But here's what I'll do. I'll tell you, I'll make this compromise. Some point over the weekend, I'll post a video. I'll run through of it, okay? That seem fair?
I'm not sure if I'm misunderstanding the gear ratio, but would making Jeff still apply if the gears were the same size?
Well, if they were the same size, right, then they would be spinning at the same speed. So you would just add them both together, right? The scaling would just be 1. The gear ratio would just be 1, right? All right, so it's basically Friday. We've got 2 minutes left. So let's wind it down, right? Deep thoughts from Dr. D. What would bother you more, right? Being hunted by a wealthy industrialist on his or her private island, or finding out that your boss has created a robotic clone of you to clean up his or her office? Which one of these things would bother you more? interesting. These are the hardcore, the hard-hitting questions that need to be answered. Yeah, it's pretty close. Oh, no, it's pulling away. Interesting thought, Cody. Interesting thought. He's not doing your job. Presumably, in this situation, you're not paid for cleaning. You're paid for doing like other work at the place, and he or she just wants the visual of you cleaning their office, I guess. I don't know. I agree. I think that would bother me more as well.
It would bother me so much if I like walked into my boss and there was like a version of me sitting there cleaning for him.
Oh, hey.
That
I'll
bothers
just ask my boss for
into the
a personal one.
All right. So let's switch gears. We'll do the end of the week. How's everyone feeling about class? The reds. If you're in the red, please come to office hours and ask me questions. Let me know how I can help you, right? If you're on the lower half of the scale. I think I said it on the first day of class. I'll say it again. I truly do want all of you guys to succeed. I'm here to help you in any way that I can, but I can't help you if you don't seek out help. This is not to be understood as I'm just gonna, give out grades, right? You're still gonna have to work for it. There is a standard that we're gonna work toward, but I'm here to help you in any way that I can. So please, if you're super confused about stuff, make sure you're coming and you're asking questions. Okay. And then,
So are you going to post like not the whole answers, but like just basically like the reduced equations is actually what I'm more looking at, because that's what's confusing me.
so for these example problems,
Yeah, sorry, I don't know if we were going to continue like to next week to do these or like.
no, I'm going to post this week a PDF with all of my hand-drawn work. All right, and that's what you're gonna get. And then next week we are switching, guys. We're going to one of everybody's. I know it's some of your favorite topics. Electrical systems starts next week. Electrical systems starts next week. So just when you thought that you had this under control, right? We're gonna change it completely. Except that it's not gonna be completely changed. You'll see. Okay. We are done. Have a great weekend. Remember, I have office hours from 3 to 5 tomorrow.
Thank you.
Have a good one.
Thank you, Dr. D.
Dr. D.
What's up?
I'm sorry. Did you say that you would also post like a video like explaining how to do some of the problems for the rest of this second week? Or is it just going to be that PDF file?
I will post a video for the last problem that we just did, doing it the long way without Jay effective. Jeff will not make an appearance. You guys did not like Jeff. Feel bad for him, but yeah, I'll post a video. I'll do it by hand, and I'll post a video on how to do it sometime this weekend. All right.
All right, groovy. Thank you so much. Have a good rest of your day.
Thanks, too.
I have a question real fast about the lab report that's due tonight.
All right.
You said you wanted a time versus position graph.
Yes. Yes, please.
So you want us to like go back through, watch your YouTube video and like time like multiple positions for each trial, or?
Yes, for each trial.
Okay.
You said only one person had to submit it, right?
What's that? Oh, sorry.
You said only one person had to submit the lab report?
Yeah, I only need one of you to submit it. It's fine. You'll all get the feedback, so don't worry. Right? You just won't have, you'll get the grade and you'll get the feedback from the lab. You just won't have the lab in your Dropbox. It's the only difference.
Professor, we have I have a quick question. So, do you have any, I mean, I know you have no office hours today, but I was wondering maybe if you had time in between your classes today.
I've got another class in 10 minutes right now. And then
Okay.
this class after this is supposed to start right at 3. So there's really not a lot of time today. Tomorrow I do have one from 3 to 5, but I know trying to get lab help, that's not really, probably not helpful.
Okay, yeah, because the question I was gonna ask is actually in relation to the lab that's actually due tonight, but
Okay. What's your question?
so basically because let me see if I can pull up the graph. I don't know, but we came up with like the graph and all of it, but the way it looks, I mean, personally, I don't think it's supposed to look that way, but I just wanted to double check with you to
Look
see
like
if,
a bunch of peaks and valleys.
yeah, something of that sort, yeah.
So what probably happened is, what's your time scale? How often did you take data?
5 seconds, 10.
That's probably why.
Okay.
Because so it's the difference between an analog and a digital signal, right? Your sampling rate is very low, right?
Okay.
And so you're getting swings on both sides and you're taking points, right? And
Yeah.
you can make that work with your data. You don't have to go back there and redo any of that. But you need to discuss sources of error as to what we would do differently next time, right? So if you had taken data at a much more frequent pace, right, somewhere under a second, right, somewhere under 1 hertz, you would have gotten a much more granular curve, right?
Okay.
So that's just stemming from your choice of sampling rate.
Okay, all right. I also had a question. Yeah, go ahead.
Oh, sorry, I just wanted to ask if you would like take points off it for the time.
For the graph?
So explain your error, right? So part of being an engineer is things aren't gonna be nice all the time, right? Things don't always work. You need to analyze why it didn't work and how you can make it work the next time if you're gonna do it. So that's a large part of this laboratory.
Okay.
A lot of places where error can creep in here. There's a lot of places.
Okay, then I have one last question. Was the lab in any way, maybe say in relation to like the period or maybe like in terms of the length? Because I mean, like, I know it's solely about the angular position and time, but well, actually while going through the whole thing, I just wanted to know if period and length, actually played some sort of role in it.
Just say it one more time. You cut out for a second. Period and length are what?
Yeah, so I mean, I just wanted to know if those two quantities were like in any way related to the lab, or like we just like had to solely base, like all the or maybe like, so maybe say just lay more emphasis on like the angular position and time, or like, we had to like maybe be able to come up with the period maybe for like say each of the trials that we actually did.
Right. So you don't need to do anything with period. If you have
Okay.
in terms of position and time, that should be sufficient, because that's how you're going to compare it to the Newton's law model that you have, right? So that's part of it.
Okay. All right. Thank you, Professor.
Thank you.
Dr. D.
Yeah, what's up?
So I was talking to Sean. I was finally able to contact him yesterday. And he told me that apparently he actually found a group during the weekend and he forgot to tell you. So should I just do it by myself?
Yeah, I guess at this point, you should probably just do it by yourself then. And then before next lab, make sure that you touch base with somebody to get a partner.
Yeah.
All right.
All right. Thanks.
Yep, no problem.
Yeah.
For sure.